Hey, so this is Joe, and this is the fourth video in the 11th chapter of Stewart's Calculus, and this is kind of the general series video part 2. So if you haven't looked at part 1 or the video on alternating series, I'd recommend watching those two before jumping to this one. But in this video we're going to be covering the convergence and the divergence of alternating series and the tests you can do to figure that out. We're going to be talking about absolute convergence, and then we're going to be talking about the ratio test and the root test, both of which test absolute convergence of different series. So let's start off with talking about an alternating series. What is an alternating series? Well, an alternating series is a series in which the terms alternate between having positive and negative signs. So one term will be positive, the next will be negative, and they take forms kind of along the lines of this. So we've got some series a of n, and it's multiplied by a -1 to an n, or an n plus 1, or an n minus 1 that just changes the order in which terms are positive and negative. So when we expand this series out, we'll get, so starting at 1, -1 to the 1 is going to be a negative, so it's going to be negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 minus a sub 5, and on and on and on. So that's kind of how an alternating series works, and they're a little bit different for finding the convergence of that series, because the terms alternate, and sometimes they diverge, but more often the normal series they'll converge, because you add some values, and then you subtract a little bit, and then you add, and then you subtract a little bit. So you can't always just use the same tests that we've been using this whole time for finding the convergence of series. For example, the integral test, one of its preconditions is that the series be positive. Well, an alternating series is not a positive series because you have negative terms. So we need to have a couple of tests to test the convergence of alternating series, and luckily we have one that's actually called the alternating series test, so it's kind of obvious when you're going to be using that particular test. So our alternating series test says that if we have some alternating series in the form of -1 to n plus or minus something times a series b of n, or a sequence b of n I should say, if the series of just b of n is decreasing and the limit as n approaches infinity of b of n equals 0, then the alternating series with b of n is convergent. So that alternating series is convergent, and that is how we test the convergence of alternating series. However, this doesn't tell us that b of n is convergent. It just tells us that if b of n is alternating, then it's convergent. So what do we call a series that when it's alternating is convergent and when it's not alternating is convergent? Well, we call that absolute convergence. So we can also phrase it as when a series and the absolute value of that series are convergent. So if we're talking about the convergence of a series that's not alternating and only is positive, then it is absolutely convergent. However, that's not really saying much. Absolute convergence is really important when it comes to alternating series or series that end up going negative every once in a while. So for example, some series using trig functions, and so then it's absolutely convergent when we have the series and its absolute value are both convergent. However, the alternating series test doesn't test for absolute convergence, it just tests for the convergence of the alternating series itself. But luckily, we have two tests that we can use to test for absolute convergence. They're called the ratio test and the root test, and they do just about the same thing, but I'm going to talk about both right here. So the ratio test says that given some series a of n, if we take the limit as n approaches infinity of the absolute value of a of n plus 1, so that means given our expression of a, and we add 1 to all the values of n, and so we use the term greater, over a of n, if that equals some limit, and that limit is less than 1, then we say that this series is absolutely convergent. And if that limit is greater than 1, or if the limit is, actually it could never be negative infinity because this is the absolute value, if the limit is infinity, then the series is divergent. And If the limit's equal to 1, then the test fails and it's inconclusive and we can't learn anything new about that function, convergence or divergence wise, and you'll need to use another test. And now the root test, and so this test, because there's a ratio, you'll end up being able to cancel out things in the expression for the series. So it's very helpful, and it's basically the only test you should use for series that have factorials in them, or series that have powers that could be easily canceled. But aside from the factorials, really this test does just about the same thing as the next test I'm about to show you, which is the root test. Alright, and so the root test says that if given a series A of n, if the limit is n approached infinity of the root to the nth power, so of the absolute value of a to the n, or we could otherwise write this as the limit as n approaches infinity of the absolute value of a sub n to the 1 over nth power. If that limit exists and is less than 1, then we say that the series is absolutely convergent. If that limit's greater than 1, or the limit is equal to infinity, then the series is divergent, and same as the last, and so all these limit conditions are the same as with the ratio test, or if that limit is equal to 1, the test failed. And so I want to just kind of reiterate that these tests are super helpful when we're talking about alternating series and finding absolute convergence, but they're also useful for finding the convergence, or I guess the absolute convergence, for any series that you would be able to use the integral test for, because if a series is positive and it's convergent, then the absolute value of that series is also convergent, so it's absolutely convergent. So you can use the root test and the ratio with pretty much any series, which make them very, very helpful tests. So let's actually try a couple of those and deal with a couple of alternating series as well, and some practice problems. Alright, so let's start off with number 12 on page 755 in your book, and we get the series. So it's an alternating series, -1 to the n plus 1 power. That makes it alternating. Each term is going to be either positive or negative, and they'll alternate like that. And then the series is n times e to the negative n. And we're asked to figure out whether this alternating series is convergent or divergent. So the first test we should do when we get an alternating series like this, because it's going to be the easiest, is just the alternating series test. Because this question doesn't ask us to figure out if it's absolutely convergent, it just asks us to figure out if it's convergent or not. And the alternating series can tell us, alternating series test can tell us that. So the absolute value of this series is just going to be this part without the negative aspect on it, which is what this -1 to the n plus 1 does for us. So we're going to find the limit as n approaches infinity of n times e to the negative n. Now we can rewrite this out as a fraction, which is easier to take the limit of, because we can end up using L'Hopital's rule. So we get n over e to the n. We plug infinity into there, we're going to get our indeterminate form infinity over infinity, which allows us to use L'Hopital's rule. So then we get the limit as n approaches infinity, the derivative of n is 1, the derivative of e to the n is going to be e to the n. But since this is in the denominator, yeah, so it's going to be 1 over e to the n, and we put an infinity in here, that's going to be a 0. And so that means that the series converges. And so that's by the alternating series test. So that's pretty simple. That's a pretty simple form of and way of finding the convergence of an alternating series. Alright, so now we're going to do number 6 on page 761, and this question asks us to figure out whether this series right here, this alternating series, because we've got a negative to the n right there, asks us to figure out whether this series is absolutely convergent, or in other words, conditionally convergent, or divergent. And so we can't use the alternating series test because it won't be able to tell us if this is absolutely convergent. We've got an alternating series, so that means we're going to have to use either the root test or the ratio test. And we've got a factorial down here. And so as I said, the ratio test is really helpful for a series with a factorial because you can actually eventually end up canceling out this factorial here because for reasons that I'll show later for kind of algebra tricks you can do. So we're going to use the ratio test, and so the ratio test involves, let's just write this out here, finding the limit as n approaches infinity of a to the n plus 1, and this is the absolute value, over a to the n. And so in this case, if we take this to be a to the a sub n, and the absolute value is just going to be this series without that negative, we're going to make that little negative a positive, then in the numerator, we'll just have to add a plus 1 to all the n's we see. So it'll be 3 to the n plus 1 over 2 times n plus 1, all of that factorial, and then divided by, so I'm just going to multiply by the reciprocal of a sub n, so this is going to be 2n plus 1, factorial, and then 3 to the n. So, and this is, of course, the limit as n approaches infinity. And so now we can start simplifying. 3 to the n plus 1 is really equal to 3 times 3 to the n, and 2 times n plus 1, we distribute that 2, we're going to get 2n plus 2 plus 1, so it's 2n plus 3 factorial. And over on this side, we're still going to get 2n plus 1 factorial, and we'll get 3n. And so the little algebra trick that makes the ratio test so great for canceling out factorials is 2n plus 3 is really 2n plus 1 factorial times the next term, which is 2n plus 2, plus the next term, which is 2n plus 3. And so we'll end up being able to cancel out that expression here. And already, we've taken out the 3 to the nth power. We've got a 3 to the nth power right there. So already we can cancel those guys out. So we'll get the limit as n approaches infinity of 3 times 2n plus 1 factorial over 2n plus 1 factorial times 2n plus 2, which is the next term, and 2n plus 3, which is the next term, and both of those are implied by this 2n plus 3 factorial. So then these factorial expressions will cancel out, and what we're left with is the limit as n approaches infinity of 3 over 2n plus 2 times 2n plus 3. And since we've only got our n's in the bottom, when we put infinity in there, this whole expression will turn into a 0. So the limit is equal to 0, which is less than 1, which means that the series is absolutely convergent by the ratio test. And so that's how the ratio test works to figure out absolute convergence. So let's do another problem. So number 7 on the same page asks us to figure out whether this series, k times 2/3 to the k, that's a 3 down there by the way, is absolutely convergent, conditionally convergent, or divergent. So we're going to want to use either the ratio or the root test to figure this out. And since we've got a k up here, and the root test would be multiplying this entire series by 1 over k, we could potentially cancel out that k. And so the root test, for this reason, we're going to want to try to use first. And so you really want to use the root test when you've got an expression to the power of k like this, because you'll be able to cancel things out. So remember, the root test says we need to find the limit as n approaches infinity as the absolute value of the series times 1 over n. And so in this case, we're using k, so we're going to get the limit as k approaches infinity. And this is always positive, so we don't need to find its absolute value, of 2/3 to the k to the 1 over k. So we can multiply this 1 over k by the exponents of the things multiplied inside the expression. So this will turn into the limit as k approaches infinity of k to the 1 over k. And then this k times the 1 over k is going to be a 1. And so that is just a 2/3 then. And so when we plug in infinity for k to the 1 over k, we're going to get k to the 0. which is going to turn into a 1 times 2/3, because anything to the power of 0 is going to be a 1. So we're going to get the limit as k approaches infinity of 1 times 2/3, which means that that limit is just 2/3, and that is less than 1, so the series is absolutely convergent by the root test. And so that is how that test works. We're just going to be doing 2 more problems, because this is kind of an important thing to practice in terms of applying which test when. Number 23 asks us to find whether the series 1 plus 1 over n times n squared is conditionally convergent, absolutely convergent, or divergent. And so since the whole thing is to the power of n, it makes sense to try out the root test first. So let's do that. So we're going to get the limit as n approaches infinity of 1 plus 1 over n squared, and all of this to the 1 over nth power. And so one of these n's will cancel out, and we're going to get the limit as n approaches infinity of 1 plus 1 over n to the n. And so you could continue to do some limit work here, but if you remember, this limit is our definition of e, the constant e. So we can just write out e. We know e is a little bit greater than 2, so that's greater than 1. So therefore, this series is divergent by the root test. So that's a pretty simple problem, but this definition, I think as I said earlier, now you kind of know why, is really helpful just to memorize, because this will stump you on the AP for sure. Alright, so last problem coming up, just a second. Alright, so now we've got the series of 2 to the n squared over n factorial, and so we should and we want to find out whether it's conditionally convergent, absolutely convergent, or divergent. And since we've got a factorial here, we should probably be using the ratio test. So, and it's not alternating, so finding the absolute value, well, we've got it right there. So we're going to find the limit as n approaches infinity of 8 sub n plus 1, so we're just going to add a plus 1 to all these expressions. So we're going to get 2 to the n plus 1 squared over n plus 1 factorial, and then we're going to multiply by the reciprocal of a sub n, and we're going to get n factorial over 2 to the n squared. So now we're going to expand out this this exponent and this factorial right here. So we're going to get the limit as n approaches infinity of 2 to the n squared plus 2n plus 1 over n factorial times n plus 1, and then all that times n factorial times 2 to the n squared. And we can expand out this, so already we can cancel out our factorials first off, and then we can expand out that expression right there, and we're going to get the limit as n approaches infinity of 2 to the n squared times 2 to the 2n times 2 over n plus 1 times 2 to the n squared. So our 2 to the n squareds are going to cancel out, and we're left with the limit as n approaches infinity of 2 to the 2n times 2 over n plus 1. And now we can start using L'Hopital's rule. So, because when we plug in infinity here, we're going to get an infinity over an infinity, and that's our indeterminate form. So, we're going to get the limit as n approaches infinity, and we're taking the derivative up here, so that constant remains. We're going to get a 2, but we also have to take the derivative of the exponent, so that that coefficient is going to become a 4. We leave the 2 to the 2n, and we take the natural log of 2, and then the natural log of the denominator, the derivative of the denominator, sorry, is just going to end up being 1. So we don't need that the fraction bar. So we're just going to get this. And then when we plug in infinity, we're going to get an infinity. And so, obviously, that's greater than 1. So this series is divergent by the ratio test. So that's it for this video. That's kind of all that now you have in your quiver, like all of the tests you're going to need really to test convergence and divergence of series. And then so now we're going to dive more into finding intervals of convergence for power series, and then eventually into Taylor series. Then I guess we'll call it Calc BC then. So thanks for watching, and get excited for the rest.